In this video, we will first look at what happens when we take the dual of the dual LP, and then we'll discuss the rules for forming the dual of a general LP that involves all types of constraints and can be either maximization or minimization. Previously, we discussed how we form the dual for a maximization problem in the canonical form. Here it is written for the general case. So let's go over this exercise again and formulate it using the general algebraic notations. So we start by introducing the dual variable for each constraint. So you'll have the dual variable yi corresponding to the constraint I here. And then the way we write the dual, since the primal is maximization, the dual is going to be minimization. And now the right-hand side of the primal becomes the coefficients in the objective of the dual. So we have the summation of bi's, yi's for I between 1 and m. And we have the following constraints. So the constraints are formed by looking at the columns of the primal problem, and for each column, for each variable of the primal problem, we will have a constraint in the dual problem. And if you look at the columns for the primal problem, you have aij's, and we fix j when we look at the column. So you look at the column corresponding to the variable xj, and then I will go from 1 to m. And we multiply aij by yi, and we sum up over I. So the summation is going to be for I between 1 and m of aij's yi's, and this must be greater than or equal to cj. And this is for j between 1 and n. And finally, we have the non-negativity, yi's are greater than or equal to 0 for all I between 1 and m. So here is our general dual LP for a primal maximization problem in the canonical form. We call xj's the primal variables, yi's are the dual variables, and here we use the indices j for the variables of the primal problem and I for the constraints of the primal problem, and as a result we have i's for the variables of the dual problem and j's for the constraints of the primal problem. Alright, so whatever used to be variables now becomes constraints, whatever used to be constraints becomes variables when we switch to dual. Alright, so let's look at the same primal maximization problem in the canonical form. And we just formulated the dual of this LP, right? So now, what if we try to formulate the dual of this dual LP? So this is our dual now, it is in the canonical minimization form. And what we are going to do to formulate its dual, we are going to convert it into a maximization problem in the canonical form. So for that, we are going to multiply the objective by -1, and then we are going to multiply both sides of every constraint by -1 in order to obtain an equivalent problem, which will be maximization in the canonical form now. So we'll have maximize -w given by the summation for I between 1 and m of negative bi's, yi's, subject to, and now I'm multiplying both sides of each constraint by -1, the summation for I between 1 and m of negative aij, yi is less than or equal to negative cj for j between 1 and n. And we also have y1 through ym is greater than or equal to 0. Alright, so this is now our dual LP converted into a maximization problem in the canonical form. Alright, so here it is once again. And now we can easily write the dual of this LP, right? So because now it's in the maximization canonical form and we know how to write a dual for this type of a problem, So let's write a dual for this problem. First, we introduce the dual variables. Let's denote the dual variables by xj's. Alright, so now we see that the dual of the dual is in fact our primal LP. So we can now talk about two LPs being dual to each other because the dual of the dual is primal. And now we can see that if, let's say, your primal is a minimization problem, then the dual is going to be a maximization problem, alright? So there is a very, very close relation between the primal and dual problem. Now we are ready to discuss the rules for forming the dual LP in the very general case, okay? Let's think about how we are going to deal with the equality constraints. So far, we only looked at the inequality constraints when we formed the dual. We can easily convert the greater than or equal to constraint into less than or equal to constraint by multiplying both sides by -1, so we know how to treat inequality constraints. But we haven't discussed yet how we treat the equality constraints. So let's look at this example here. So the trick that we are gonna use here, we just represent this equality constraint as two inequality constraints. We will say that 2x1 plus 3x2 plus 7x3 is less than or equal to 8, and then it is also greater than or equal to 8, right? And both of these inequalities combined will be equivalent to this equality right here. Okay, so, and what we are gonna do, we will convert the greater than or equal to inequality into less than or equal to by multiplying both sides by -1. So as a result, we'll have negative 2x1 minus 3x2 minus 7x3 is less than or equal to the -8. Okay, so now once we replace this equality with the two inequality constraints, when we have this equality arising in the context of a primal problem, this is how it's gonna appear in the dual problem. So we'll introduce a dual variable for each of these two constraints. Let's say, let's denote the dual variable for the first of these constraints by y prime, and for the second one y2 prime. And then we proceed as usual, right? So the way this constraint from the primal is going to appear in the objective will be 8y prime minus 8y2 prime. So this is in the objective. We'll probably have some other terms before and after. Then for the constraints, the way it's gonna appear in the constraints, we will have in the first constraint, the part corresponding to this inequality is gonna be 2y prime minus 2y2 prime. So this is within a constraint. Then for the second constraint of our dual will correspond to the variable x2, and we'll have the part corresponding to our equality constraint from the primal will be 3 times y prime minus 3 times y2 prime. And for the third constraint, we'll have 7 times y prime minus 7 times y2 prime. Okay, so we can see that in every constraint and in the objective, y prime and y2 prime appear with the opposite signs and with the same coefficient, but the opposite signs, right? So therefore we can do the change of variable, and let's say we denote by y the difference between y prime and y2 prime, and as a result what we had before will be equivalent to, so we'll only focus on the part corresponding to y prime and y2 prime. So now in the objective, y is going to appear with the coefficient of 8. Then in the first constraint is going to appear with the coefficient of 2. In the second constraint with the coefficient of 3. and in the third constraint with the coefficient of 7. So now we see that what essentially happened here, we introduced a dual variable y for this equality constraint, and the way this dual variable y appears in the dual problem is with the coefficient of 8 in the objective and the coefficients from the left hand side of this equality in the constraints. Essentially, it's the same as what we had for the inequality constraint, but now look, y is the difference of two non-negative variables, and it can actually be negative, right? So therefore, y is unrestricted in sign. So this is the difference between the inequality and equality constraint. When we introduce a dual variable for the equality constraint, it is unrestricted in sign. Okay, so this is the key thing to remember about the equality constraint. And now, of course, whenever we have the equality constraint appearing in the primal problem, we will automatically use the unrestricted in sign dual variable to represent this part in the dual LP. And now we are ready to formulate a dual LP for an arbitrary problem. So this table here summarizes the rules for forming a dual. And this assumes the primal maximization problem. So then the dual is going to be the minimization problem. And when we have the equality constraint, we will have the unrestricted in sign variable corresponding to this constraint in the dual problem. Then if we have the less than or equal to constraint in the maximization problem, then this will correspond to a non-negative variable in the minimization problem. Now this goes the other way around also, because we know that the dual of the dual is primal. If I look at the equality constraint in the dual, then this will correspond to unrestricted in sign variable in the primal. And if we have the inequality constraint of greater than or equal to type in the minimization dual, then we'll have the non-negative variable correspond to it in the maximization primal. Here, of course, we didn't consider the case when, let's say, I have an inequality constraint of greater than or equal to type for the primal maximization problem. Why we didn't consider this? Because what we're gonna do in such cases, we'll convert every problem to the canonical form, meaning that whenever I have a maximization problem, I'm gonna convert all the inequality constraints into less than or equal to type. I'll just multiply both sides of the greater than or equal to inequality by -1, and as a result, we will have only less than or equal to constraints and the equality constraints, and this covers all the cases, right? So similarly, when we have a less than or equal to constraint in a minimization problem, what we're gonna do, we'll convert it into a greater than or equal to type to convert this minimization problem to the canonical form, and then we'll not have less than or equal to constraints in a minimization problem. Alright, but in case you want to keep it as is, as a greater than or equal to constraint in a maximization problem, then what will happen, the sign of the variable will reverse, and you will have a non-positive variable corresponding to this type of constraint in the dual problem. Alright, but since we are used to having non-negative variables, we will stick to the canonical form and we'll convert the greater than or equal to constraints for maximization into less than or equal to, and the less than or equal to constraints for minimization into greater than or equal to constraints to keep the problems in the canonical form. Alright, so, but similarly, if I had, let's say, the inequality of less than or equal to type for the dual, then this would correspond to non-positive variable in the primal. So let's look at an example of forming the dual for an arbitrary LP with all types of variables and constraints. So we have a primal maximization problem given here. So we have the equality constraint, a greater than or equal to constraint, and a less than or equal to constraint. We will start by converting the problem to the canonical form. So for this, we need to ensure that all the inequality constraints are in the less than or equal to form, because it's a maximization problem. And again, an easy way to remember that you have less than or equal to constraint for maximization, think about having a problem of maximizing the profit or revenue subject to limited resources, and limited resources are usually expressed with less than or equal to constraints. So let's convert this into less than or equal to type. We multiply both sides by -1, and this will be less than or equal to -3 now. Alright, so next we introduce the dual variables. So we'll have y1 will be the dual variable that's unrestricted in sign because we have the equality type constraint for the primal LP. Then here we have a non-negative variable y2 because we have an inequality constraint, and non-negative variable y3. Alright, and now we are ready to formulate the dual. We'll have, the objective is to minimize 2y1 minus 3y2 plus y3. So we use the right hand sides as the coefficients in the objective here. And then we have subject to, for the first constraint we'll have, first of all we need to look at the type of the variable, right? So it's a non-negative variable in the primal, which means that we'll have a greater than or equal to constraint for the dual. So let's note this here. So for the first dual constraint we'll have a greater than or equal to constraint, and then x2 was unrestricted in sign. So let's note that the second constraint for the dual will be the equality type because it corresponds to an unrestricted in sign variable in the primal. Okay, so the first constraint is gonna be 1 times y1, so y1 minus 2y2 plus y3 greater than or equal to 2, the coefficient in the objective. And the second constraint will be of the equality type, so we'll have y1 plus y2 minus y3 is equal to, the coefficient for x2 in the objective is 1, and then we specify the types of the variables we got, right? So y1 is gonna be unrestricted in sign, and then y2 and y3 will be non-negative. So this completes the dual of this LP, okay? And let's say if we decided to keep this inequality constraint in the greater than or equal to form, then what would have changed? So we would keep the original inequality here. This would change the signs in the corresponding column of the dual, right? And our corresponding dual variable would be of less than or equal to 0 type. All right, so but it's clear that it would be the same thing, right? So, and since we typically have non-negativity constraints and everything we discussed for the LP in the standard form assume the non-negativity constraints, let's avoid the non-positive variables. So now it's time to practice again. Please formulate an arbitrary LP. Just come up with some random LP with all kinds of variables and constraints and formulate the dual for this LP.